For this next unit, we're going to be taking a look at what are known as rational expressions. And we're going to start that off with the idea of equivalent rational expressions, the idea of two expressions, whether they're rational or not, that are expressed in a different form, but they still carry the same meaning. So to do that, where we're going to start is going to be, I have a handout, it's available on the web page, I'll be distributing it to the class. And in this handout, we have a number of rational expressions. So if you're wondering what that means exactly, I'm going to explain that to you in just a moment. As you go through that handout on your own, the instructions are there. So what we're going to do is algebraically, we want to try to come up with an equivalent expression for what we're looking at. And then we want to come up with some sort of graph for the expression. You can actually do these two steps in either order, whichever one you prefer. The order I've listed here is kind of the preferred order, but particularly when you're getting started, if you want to use something like, for example, a table of values, you could do the graph first, and that might give you an idea of where you should be ending up when you do this algebraically. From the start to the end, from your original expression to your new expression, there will be some steps that we take that will result in some differences being introduced. They'll look the same, the graphs will look the same, but there will be some very important differences between them. So as you go through this, give some thought to the algebraic or the graphical differences that you might expect to see. So here's our first one, and it is the expression 3x plus 6 divided by x plus 2. Now when we talk about a rational expression, this is the kind of form that we're talking about. A rational expression is what's known as a polynomial divided by another polynomial. And in general, a polynomial, if you're not familiar with that idea, it's anything that has essentially integer powers of x. So in this case, you can see we've got 3x plus 6 over x plus 2. Those are two linear polynomials. We can also have quadratic polynomials. We can even have, although it's not normally referred to this way, we can even have a constant. So we could have 3 divided by 2x plus 1. That would be a constant over a polynomial, but it would still count as a rational expression. So let's look at the rational expression we have here. And the first thing I'm going to point out to you is that the numerator and denominator, they look kind of similar to each other. And since this is division, one of the key skills or one of the key concepts you're going to want to keep in mind when you have division is going to be common factors. If I can factor this numerator to result in a common factor between the numerator and denominator, that's actually going to help my case a great deal. In this case, I can take a common factor of 3 out from the numerator, and when we write the denominator this way, x plus 2, we don't need to put the brackets there because it's understood that the x plus 2 is in the entire denominator. But it would also be valid to write it this way. And then you could ask yourself the question, well, x plus 2 goes into itself one time and x plus 2 goes into itself one time. So those two things divide out, giving me an equivalent expression of 3. But because I factored out an x plus 2, one of the things that we have here is we have x plus 2 in the denominator, so the fact that we have x plus 2 in the denominator, that tells us that x plus 2 is never allowed to be 0. And that's the same thing as saying that x is never allowed to be negative 2. And this is an important thing to keep track of, because when I divide out those two common factors, this piece of information is lost. So this info is lost. And because this information is lost, we need to keep track of it by stating this restriction. So we say now that y is equal to 3 with the restriction that x is not equal to negative 2. So y equal to 3, what does that look like? 1, 2, 3. So there is y is equal to 3. And so this is going to be a horizontal line, y equals 3. Now you might look at this and you might be a little bit skeptical about this. First of all, about that general shape. So I'm going to come back to that in a moment. But the other thing I need to add in here is the fact that x is not allowed to be negative 2. I have to represent that in some way. So here is negative 2. And so if we were doing a table of values here, which I'm going to do in a moment, if I put in x equals negative 2, then I'd have to ask myself, well, what's supposed to go here? Because I have this information being lost. X is not allowed to be negative 2. So how do I account for that? So before I do that, let's just go ahead and work through this as a table of values instead. So here's x, and then I have y equals 3x plus 6 divided by x plus 2. So let's imagine that you tried to do this, you didn't recognize the common factor, so I'm not going to do it in a simplified form. Now I'm going to negative 4, negative 2, 0, 2, 4. That's not right. There's 2. And there's 4. So I think I'll start at negative 4. So what happens when I put negative 4 in here? 3 times negative 4 is negative 12. Plus 6 gives me negative 6. Divided by negative 4 plus 2 is negative 2. And negative 6 divided by 2 is equal to 3. What happens when I put in x equals negative 3? 3 times negative 3 is negative 9. Plus 6 is negative 3. Divided by negative 3 plus 2 is negative 1. And negative 3 over negative 1 is positive 3. If I did negative 2.5, I would end up with 3. If I did negative 2.1, I would end up with 3. No matter what value I put in here, I'm going to get an answer of 3 until I try to do negative 2 itself. 3 times negative 2 is negative 6, plus 6 is 0, over negative 2 plus 2 is 0. 0 divided by 0 is undefined. And then I carry on. Negative 1.9 would give me an answer of 3. Negative 1 would give me an answer of 3. 0 gives me an answer of 3. And so on. I just keep getting 3's. So that's where this horizontal line comes from. No matter what value of x I put in here, I end up with a y value of 3. But at this one particular x value of negative 2, I end up with a result that is undefined. And the way that we represent that, well, there's a couple of ways. One way that we've learned to represent an undefined value is with what's known as a vertical asymptote. This is not a vertical asymptote. This is what's known as a hole, which is to say that the line carries along, as shown here, basically the line from the equivalent expression, but at negative 2, and we use an open circle to represent the idea of there being a hole, just at that one value of negative 2. And the way that you distinguish between these two things, a vertical asymptote is going to occur when you have some constant divided by 0. And a hole is going to occur when you have 0 divided by 0. So this is c is not equal to 0. So this is a non-zero constant divided by 0. That gives you a vertical asymptote. If you have 0 divided by 0, which is what happens when we divide out common factors, then you have a hole. So let's take a look at another one of these and see if we can continue to make some sense of this. In this case, I take a look. Now we've learned that this idea of a common factor is very important. So I'm going to go straight into that route. Between 2 and 10, there's a common factor of 2. Between x squared and x, there's a common factor of x. The numerator is going to be left as x plus 5. In the denominator, I see a numerical common factor of 3, but no x terms that are common, so that also becomes x plus 5. Now don't just go barreling into this assuming you're going to get a common factor. Sometimes you will, a lot of times you will, but sometimes you won't. So x plus 5 goes into itself once, x plus 5 goes into itself once. So that gives us an equivalent expression of 2x over 3 with the restriction that x is not equal to negative 5. You see, from this original expression, to go from here to here is not true. This 2x squared plus 10x over 3x plus 15 is not the same as 2x over 3 unless you include the restriction. These things are only equivalent to each other if the restriction is included. And so now, from there, we can graph this. Now, you might want to write this actually as 2/3 x, and I would not normally ever write it this way, but I'm going to put plus 0 because that is my y-intercept, and this one is my slope, which means it's rise over run, and the rise is up to for a run of plus 3. So I think I'm going to use a smaller scale this time. So there's 5, 6, 7, 8, 9, 10. So I'm going to use a scale of 1 square is equal to 1. And that's going to take me to negative 10 and negative 10. And now I have a y-intercept at 0. That means I have a point here at 0, 0. This says x is not allowed to be negative 5. So what is that going to look like? We've got a run of 3, so I count 1, 2, 3 over and up 2. 1, 2, 3 over and up 2. That's my slope of 2/3. 1, 2, 3 over and up 2. And then going the other way, I go 1, 2, 3 to the left, but now I come down 2. 1, 2, 3 down 2. 1, 2, 3 down 2. And since I have this straight line tool available to me, I will connect my points with that. But at x equals negative 5, negative 1, negative 2, negative 3, negative 4, there is negative 5, and then I find out where the line exists there, and I put a circle around it, because when x equals negative 5, this becomes 0, and this becomes 0, so that's 0 divided by 0, and that gives me a hole. If you did a table of values, you would end up with a result similar to what we found in the previous one. A little bit more complicated because your table of values would actually give you points along this line, except for when x equals negative 5, you would end up with a 0 divided by 0, which would be undefined. Okay, a little bit more complicated still, so we're kind of increasing our level of complexity here. Once again, I'm looking for the opportunity to factor. In this case, because I've got a quadratic, and it's not something I can just take out a common factor, I'm going to have to use our rules for factoring a quadratic equation. This one's pretty simple in the sense that the numbers work easily enough. What are two numbers that multiply to 1 and add to 2? Or you can recognize that this is the perfect square pattern. So this is the same as x plus 1 all squared over x plus 1. Ideally, this is what you want to recognize, and you want to go to this step. If you're not comfortable with the idea of dividing out common factors, you might want to go to this, or you might want to rewrite it this way. And now, from this step, x plus 1 goes into itself one time, x plus 1 goes into itself one time. Unless you are really strong with your factoring here, I really recommend you don't cut any corners here. stroke out the different factors, put a 1 in their place to indicate how many times each one has divided into that particular factor. If you are better with your factoring, more comfortable, you might recognize that, let me write it off to the side here. If I had x squared over x to the 1, the x to the 1, what we do here is we actually subtract exponents, and that just gives us an x. So here, that goes in once, and then this exponent becomes a 1. In either case, I end up with the same result, which is I end up with y equals x plus 1, but I also have the restriction that x is not equal to negative 1. And that restriction comes from this, which is x plus 1 in the denominator is not allowed to be 0, which means x is not allowed to be negative 1. So what does the line y equal x plus 1, what does that look like? So that has, I'll go to the larger scale this time. Not for any particularly good reason, just to show you that sometimes there is no better or worse choice for scale. Sometimes there's definitely a better or a necessary choice for scale. But between this question and the one I did before, I needed this fairly small scale so that I could actually show a number of points because of this awkward slope, 2/3. Here, my slope is just equal to 1. So I've got a y-intercept at 1, which we get directly from the equation, and then over 1, up 1, over, I've lost my pen, here we go, over 1, up 1, over 1, up 1, left 1, down 1, left 1, down 1, left 1, down 1. You'll notice I'm just putting very fine dots in place this time because I don't want to put in a thick dot and end up with a dot where I'm supposed to have the hole. So I take that, stretch it out. So there is the equation of my line, and now the hole occurs at x equals negative 1, which is right here. And so I put in a open dot at that point, and that represents the hole. Now sometimes you might also be asked for the coordinates of the hole. And if you're asked for the coordinates of the hole, then you're going to give both the x coordinate and the y coordinate of the hole. Now you might say, well, hold on, I'm not allowed to have a y value there, it's undefined. And that's true for this original graph. But the location of the hole, which is at negative 1, I can take this value of negative 1 and plug it in here, and that tells me the location of the hole, which is at the point negative 1, 0. The point negative 1, 0 doesn't exist on this graph, but the point negative 1, 0 does exist on this grid. There's nothing that says that I can't identify that particular location, and that's what I'm doing here. Okay, a little bit different, but similar to what we did in the previous one. I'm going to rewrite the numerator as x minus 2, and I'm going to recognize a difference of squares in the denominator. And that gives me x minus 2, x plus 2. Now this is going to give us a new result. New in the sense that it's not something we've talked about so far. I've got common factors in the numerator and denominator, and those divide out, becoming 1s. That gives me my new expression, 1 over x plus 2, and I have to make note of the restriction that has been added here, which is x not equal to 2, and that is going to be a hole. But I have another restriction that I need to make note of here, which is this denominator, because it's not allowed to be negative either, and that gives me x equals negative 2, and in this case that is a vertical asymptote. So just as I just as I said in the previous note, if I have a situation of 0 divided by 0, that gives me a hole. And if I have a situation of a constant divided by 0, that gives me a vertical asymptote. So what is the graph of this going to look like? Okay, 1 over x plus 2. So I need a vertical asymptote at x equals -2. So once again, I'm going to put on my scale here. I think that once again, I'm just thinking from I think I'm going to do that small scale again. So there's -5, out here to -10, +10, +10, and -10. This time, as is often the case, when you have a vertical asymptote, you're going to be well served if that's what you take care of first. So there is my vertical asymptote, which occurs at x equals -2. I have a hole at x equals 2, but there's nothing more I can do about that for now. And I'm not going to get too much into detail about this, about the graphing of this. If you remember your transformations of the rational function, so what if I, as an aside, what if I said something like let f of x equal 1 over x, which is just the plain reciprocal function? Then we know that this has asymptotes along the x and y axes, and it looks like this. It looks very roughly like that. It's not a great sketch. And so now what would I need to do to end up with 1 over x plus 2? How would I take f of x and turn it into 1 over x plus 2? That would be f of x plus 2. And then what transformation is this? That is a shift to the left by 2. And so you can see, first of all, we've already covered that because here's my asymptote. It's been shifted to the left. But the reason I wanted to explain this was also to explain that the horizontal asymptote is still where it was before, which means it's along the line y equals 0. And then the other thing is that the overall shape of the graph is going to be the same. Now, in this case, again, let's locate the hole. So I'm going to ask, where is the hole coordinates? And so the hole coordinates are going to be, I'm going to sub x equal 2 into y equals 1 over x plus 2, which is 1 over 2 plus 2, which is equal to 1 over 4. So the point 2, 1/4, that's the location of this hole. So over here, +2 and 1/4, well, that's going to be really close to the x-axis, so it's going to look something like that. And then other than that one point, I could put in some other points as well. For example, we know that the point 1, 1 has been shifted over by 2. We know the point -1, -1 has been shifted over. And so now I'm going to just draw down to the asymptote there. And this is going to be tough to do nicely, but I'll do my best. Not great. Actually, I'm going to give myself a second chance at that one. That's a little bit better. And down towards the asymptote. And off to the side. I did a decent job on that one. So not only do you have to go through all of this work to find things like the new asymptotes or locations of holes, but you still have to deal with other things that we've covered previously in the course. For example, an understanding of the basic shapes of parent functions, and also being able to take a simple equation, a simple modification, and come up with transformations of that, just so that you can do this with confidence. Otherwise, you're going to end up having to do this using a table of values, which is quite time consuming. Okay, so what are some of the things that we did here when we determined our equivalent expressions? Um, One of the big skills we made use of was factoring. And the other thing we had to do was, after we factored, quite often we had to um, solve an equation. It is usually a simple equation. For example, if I took x plus 2 over x plus 2 and it became equal to just 1, I would also have to solve the equation x plus 2. It's actually called an inequality, but if I solve the equation x plus 2 equals 0, that means x equals negative 2, which gives me x not allowed to be negative 2. What else did we do? We could have used a table of values, and we actually did use a table of values at the beginning. And what were some of the other skills that we made use of here? We made use of parent functions and transformations. And there may be others. This is really just a question to get you thinking about what are some of the things that we did to lead up to those various graphs that we showed. Okay, what kind of features are going to appear on the graph? The big ones are going to be holes, of course. I would say that has been the primary focus of this lesson, is to identify these holes and see how you're supposed to graph them. And then vertical asymptotes, and sometimes with a lot of these graphs, by their very nature, you will also get a pairing of the horizontal asymptote. That's why it's very important to uh, that's why it's very important to know the transformations of the rational function. Another thing, not to go into too much detail here, but first of all, the holes, that's x and y coordinates. And then, of course, simple things like being able to make use of, if a straight line, a slope, or we might have a parabola. You need to be able to graph those comfortably. We didn't see any instances of parabolas, but they can come up. Okay, so when we do this, our equivalent expressions, the graphs look the same, but they're also different. So how can we tell the graphs apart? And this is the big difference, which is the restrictions. Okay, so if you do these with a table of values, you're going to get that same shape. If you do it using algebra, you're going to get that same shape. But the big key here is going to be the restrictions, and the restrictions are going to be represented graphically as either holes or vertical asymptotes. Now, if we're using written notation, then how do we distinguish between the original? So once again, this is going to be restrictions, so I'm not going to write that down this time. And here we have some practice to help you work through this. Questions 1 through 3 are fundamentals, quite straightforward, but you might want to, I would recommend you read through those and try to do some in your head. And if you can't, then maybe you need to do these on paper and take your time. Otherwise, if you feel like you have a good handle on these things and you kind of breeze through 1 through 3, jump on to the ones written here in black. And just a warning, question number 16 can be quite challenging, so don't expect that to be easy, or you may not get a solution to that one. We can take it up together in class.